give it a go. Type G.
Letter G is supposed to unlock flight, correct?
Yeah, letter G and up.
Hi everyone.
Is there a specific up button, or is it just forward pointing up?
G, letter G.
G, but you have to look up. You have to look up and walk towards where you're pointing.
It doesn't seem to work. Yeah, it doesn't seem to work for some reason.
Nope.
Okay, let me try
Should I
one more
promote
thing.
everyone?
No, that's alright. Just let me try one more thing. Try now, Ryan. No, G.
Yes, I'm here.
It should when you hit G, does it show fly enable at the bottom?
It does not show any messaging when I touch it.
Ah.
Say again.
Sent both links to John.
You did.
I don't understand that.
Like in the calendar and stuff like that, but I was like,
there it is.
Ah, yes, there you go. Ashley, you are echoing. Yes.
yeah, I think Maggie's
I can email them again.
talking in the.
Okay, that works. Good. Ryan,
Thank you, Pierre.
you're good to go.
Wonderful.
Yes.
Many thanks.
Thanks, FT. Il y a un double...
Tout le monde est off.
Il y a un double... En fait, il y a une conversation parallèle sur Discord.
Ah, ok. C'est pour ça que tout le monde est off ici.
T'as tes écouteurs là sur les oreilles?
Ouais, tout à fait.
Ouais, ça fait quand même de l'écho, ouais, ça fait quand même de l'écho, c'est bizarre.
Chez moi?
Je
Tu sais
sais.
pourquoi ça fait de l'écho chez moi? C'est parce que c'est vide ici. Carlos m'a déjà fait la remarque l'autre jour, la semaine dernière, et c'est parce que comme il n'y a rien ici, quand je parle.
Mute, Arthur, stop, là, que ça fait de l'écho dans tous les sens. Let's mute aussi.
Should we spread out to some of the different kiosks also in case people spawn in? I think we just lost Joan. Oh, there's John. Can anyone hear me?
Yeah, I can hear you.
Okay. There should be like 3 kiosks. Maybe we should spread out in case people spawn in.
Yep.
Isabel, do you want to stay at this one and I can look for another one?
Yeah, that sounds good.
I'm gonna go.
Maggie, John's gonna spawn into the room now.
Say again?
John is spawning into the Earth Gallery now.
Okay. Yeah, I saw that he showed up. Oh, is that an NMC the robot? Oh, that's Joan. Okay. Joan is by one of the kiosks.
Hey,
And she
John.
just changed her avatar.
John's on this side, Maggie.
Where's John? Hey, John. Ashley, should we try and fix his avatar?
Like all good, Ryan can fly both worlds.
Thank you, Peter.
John, can you hear me?
Ah, Joan is there.
Sorry, we're talking in the meet as well. So
Oh,
it's-
okay. Cool. No problem.
He's muted right now, Joan.
He's in the Google Meet.
Mm.
I'm just gonna hang here.
Right, maybe I'll go into another spawning point. Mm. All good for you, Veronica? No other question in the meantime?
I'm sorry, say that again?
Just checking in to see if you have any other question or if it's all good for you.
Yeah, no, I'm good. Thank you for checking in. I am having trouble with the audio in Discord, so I'm gonna just keep it deafened. Are you guys
Yes.
talking in the meet also, or like
No,
should I
no,
be in
I'm-
there as well, or are we just good
No, I
in the
think
gallery?
enough communication medium.
Yeah, right on.
Let's stick to this one. I think that's good.
Got it.
And you have the sound. Your sound is pretty good. So
Oh yeah,
I think-
yeah, I'm fine. I've got the gallery and headphones, so I am solid.
Yeah, no, I think it's good. So, are we gonna try to get the visitors putting
Can
the
anybody
name
see?
correctly.
Can anybody see John's
And,
avatar as a
or-
handsome dude?
I think it's good if they can put their name right, no?
Yeah, so as people
Where
come in,
is
I'll just
the US?
double
Right
check with
next
them.
to
Now,
us
I don't
here.
think I have the document
next
that
to
they were talking
Sabrina.
about, but I can kind of type into chat like who's here based on what they put into
Here's Joan.
the name. But I can show them how to
Cam1.
kind of change name and avatar. I can kind of direct them to the interface and all that.
Hi, I don't see you, but I'm here.
Oh, there you are. Yes, you are that handsome dude.
Hope you can hear me.
Excellent.
Cool.
Great
There
work,
we go,
John.
someone's coming. So
You did
there
it.
we go. So maybe you take care of this spawning point, and
Yep.
I don't know if there is one in the other one. I'll go to the next one.
Can you see on my meet? I'm
Very good.
I'm screen sharing, and you can see yourself. But if you go to the Meet, Google Meet, I'm
Hello.
sharing my screen with you, and you can see what you look
All
like.
good for you?
because I'm looking at you.
Yeah, I hope so.
Yeah,
I
yeah,
see
you sound
here.
you sound good. So there we go. I think we are
Okay.
Yeah.
good to go.
Yeah, I will just stand here to, I think people will come in around here. So
Yeah,
All
there
right,
is
well,
there is
great. So
three
I think we're all
spawning
set.
points
We should probably
next to these
jump
little
off
pebbles,
of Google Meet.
okay.
and we can
because I
welcome
think we're
people there.
echoing because
I also
there's
place
two
these
forms
little
of
graphics
communication now.
to help people in your back behind you, to help people if they show the keys and the button if it's easier with some visuals.
Yeah. I mean, I can stay on Google Meet with you, and you can unmute here
Yeah.
anytime you want, or anytime you just want to talk to just me.
Right.
So I can keep the Google Meet up if you'd like. Oh, you're muted in the Meet, but I can't hear you in the hub either. That's weird.
I'm gonna try to see if I can say hello to John Matter.
So now I'm unmuted in the hub. I'm looking at you, Ashley.
Yes.
I think, isn't that you?
Yes, this is me.
Yes. Yes, this is me.
Oh, I can mute here in the. There we go. Okay, I'm muted in the Meet. Are you feeling comfortable with walking around, John? Feeling pretty good?
Yeah, well, it's moving around and I'm not
Oh,
doing it.
it's moving around and you're not doing it.
I don't know where I went. I was not aware of doing this. I'm in a little green square here.
Hi, Ashley.
Yeah, I see you now.
Hi.
Okay, where do I need to go now?
Right now you're just hanging out while the guests arrive. Eventually we'll put you into the sky room where your talk's going to be. But that's not until.
Okay.
Ashley to Carlos, I'm hearing voices on the live stream.
I'm here. Hello. Pierre, after the show starts, I'm going to move over to Treehouse to give directions to Ryan. And you have access to that. Yes. You can push it up on your Discord so it's up at the top and you can put it next to Ashley. So if you have to jump over and tell us anything. Sounds good. I'll do that. Okay.
intro or Maggie can do an intro, either one.
Yeah, maybe it would be good if you, I don't know, if you go in front of your corner and do a quick intro.
Yep, cool.
This is mine. I just changed the ending to this.
We'll follow you there.
If you have any questions, feel free to mute yourself.
The ending was different, and now
What?
because everything I kind of changed it up.
Let me know when to go, Carlos.
Go ahead.
Okay, hi. Welcome, everybody. We are right now in the Earth Gallery of Unfolding the Universe. Hi. Welcome, everybody. We are right now in the Earth Gallery. Hold on, I'm getting mad feedback. Okay. And my name is Ashley Zelinskie. I'm the artist that created the space, along with my Can you hear me? Okay, hi, sorry. Technical difficulties. And we're back. Hi, I'm Ashley Zelinskie, and I'm here in the Earth Gallery today. The Earth Gallery is a bunch of artists that were able to come to NASA Goddard back in 2016 and actually see the James Webb Space Telescope in its clean room. And so many people were inspired and made artwork about this experience. And so this gallery is a collection of the artwork that was made inspired by that day. Due to COVID, we can't do in-person art galleries anymore due to safety measures. So Pierre and Ertu at Metaxu Studio and I formed a team, and we built this VR space so that we can all enjoy the art inspired by the James Webb Space Telescope, even in times of COVID. So you can walk around the space, look at the artwork. There are a few of the artists here tonight that they can tell you about their experience of seeing the James Webb Space Telescope and what inspired their artwork. And then at 7:30, we will be moving into the Sky Gallery. And the Sky Gallery is where my artwork, my installation work, art that I made inspired by the James Webb Space Telescope will be. And that's where John Mather is going to give his talk and teach us a little bit about the mission and his experience of being the main guy. He's the dude tonight. He's an inspirational Nobel Laureate and just all around great guy. And he's going to tell us all about the James Webb Space Telescope from start to finish. So I'm very excited to have him here with us tonight.
He's right there.
Where is he?
On your right.
Oh, there he is. Hi.
Yeah, I went wondering around. I got lost.
There he is. The man of the hour. In all his avatar glory.
So yeah, we're just gonna hang out for a little bit longer. Maybe we can walk around and meet some of the artists and look at some of the artwork. And then at 7:30, we'll go into the Sky Gallery for John's talk.
If you have any questions about my art, I'm Joan Lok, who created the embroidery. Thank you.
Woo! Got a giant happy face.
Great. Looking good. Where's the introduction?
Yeah, I tried. It like cut out at some point, but I'm also losing my voice, so I'm trying really hard to make it as short as possible.
So we can still, I mean, there is only 11 people in the room right now.
Yeah, maybe I can ping Maggie.
Yeah, we can definitely welcome.
People are complaining about the sound on the YouTube. Can we get that message to Carlos?
Yeah, they said the sound was really bad.
Yeah.
There's a lot of echo.
But I don't know if that's just positional right now.
Yeah, so maybe maybe it makes it tricky to get the sound. Could cause some problem if we have it's echoing from somewhere.
The sound was okay. It just sounded like someone's speakers are on while the stream is going as well. Echoing.
Feedback. I could hear myself.
John, I switched to headphones. Is that better?
Oh yeah, maybe that was it. But
I can hear you.
Yeah, I can hear you fine, John.
Yeah.
Okay.
Yeah, headphone is pretty good. We have an unknown person.
Hello. We can grab him and see who he is. We have 11 people in here. We can add more, Maggie, if you want to start filtering more people in.
Yes, I think definitely
Should
we
I
can
send
have more
people
people.
on the wait list?
Yeah.
Yes, I would.
Okay.
We have only 10 people right now in the room. We can have 10 more easy.
I'll look at the wait list. I tried to talk to the two people who were unfamiliar, but neither of them responded, so I don't know who they actually were.
Okay.
So I don't know what's going on with that. But I can try to, through Eventbrite, I guess, send out some emails to the wait list.
Yeah, sure.
Okay.
And Ashley, did you get me set up with the megaphone you were talking about so everyone can hear me? You did.
Yeah, we got your megaphone. Once you're on the stage, you can use your megaphone. Anybody on the stage can use the megaphone. That's how we set it up so that Maggie can introduce you too.
Ah, okay. Sounds like almost real.
Yeah, it's close to real as we can get it right now. So Pierre, let me know when you want me to bring John over to the other space and get him set up, because we're at 7:19 right now.
Ashley, how many people should I release tickets to?
Maggie, I would do everyone.
Okay.
think I would. I think did I hear that you invite everyone else? I think it's a good idea because even if they can't get into the space, they can still watch as spectators as well. So I would invite everyone who have on your waiting list.
So I released the tickets, but I'm not sure how to email them the link.
You don't have. You must have their email, no? From the. Welcome, Michelle. Is that working for you? Can you hear me?
Yes, I can.
Yes, great. You came in and then you had to leave, no? And then you came back.
No, this is the first time I'm coming.
Oh, okay. If you have any questions, let me know. I'm the designer of the virtual environment.
Oh, right.
And there are a few of the artists in the space as well.
Cool, I'm a friend of Ashley.
I've been working with Ashley hardly for the few last months. So yeah, the space is very big, so I'll let you explore, but I think everyone is on the other side. So.
Okay, I'm gonna walk around a bit then.
Yes, sounds good.
Okay, I think I sent out waitlist email. There's a separate setting for waitlist ticket release message. I resent that with the VR gallery link.
more people are coming in.
Hello. Oh, I'm Joan Lok. You were looking at my art just a minute ago. Hi, Michelle.
Oh, hi, John. How's it going?
If you have any question about my art, let me know.
All right. Which one is yours?
Oh,
here it is. Here it is.
Yeah, this I have 4 pieces. The one you're looking at
We're
is
getting like some major echoing. I can hear Joan.
Ooh, can we answer any questions for you?
Sure.
Hi.
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 Welcome. I'm Maggie.
Hey, John. Do you want me to take you into the other room now and help you get ready? What's up,
Sure.
Michelle?
Okay.
What's up?
Wait, I'm
Here
always
it goes.
going away.
She just left.
Do I look like an astronaut?
Yeah.
You do.
You do.
Cool.
I actually have a headset, but it's not connected to the computer. And if you hover over it with your little
Wait, you're using a headset or are you using a computer?
computer, but and if you I thought I can actually use a headset. Fran is here.
I have not seen her. I was just looking at Joan's art.
Oh, okay. What's up?
Not much.
Not work. What's the deal with Peloton right now?
Pretty shit.
Why? What's happening?
I just found out my green card process is basically gonna have to reset because of the stupid layoffs.
Why? Why does it have any connection?
Because the green card works in a way that they need my green card because they cannot find anyone, right? To do the job. But they fired some people who had my job. So in the eyes of the immigration, like this makes no sense. They're firing people, but like I'm irreplaceable.
Yeah, I'm confused. Should we try to get people to the other gallery? Or
Guys, we can hear you on the stream.
Are we moving to the other gallery already?
I don't know. It's 7:30 almost. So there's a couple over by Joan and Veronica.
Let's not talk about green cards.
Michelle is
Yeah.
here.
Bad topic.
So
We get them to the other gallery.
Yeah, we can. So the link is behind you. Everybody can go and click on the link there, you know? If you follow me.
Where is Ashley's stuff?
I don't know. I was trying to walk around and find it.
Right. Should we tell them to?
I don't think
confirm
it's
it.
the whole
We can
round.
enter the other gallery by clicking on the link here on the
Michelle and
Right. Should we ask Ashley? Or I don't know if she's in
we
the
are
other
moving to
gallery.
the Sky
John,
Gallery
probably.
now.
Oh, I don't know if they want us there.
Yeah, which is
Let me quick
just
check
follow
this.
me, I think.
Okay.
Sky Gallery is here.
Yes.
Right there.
Perfect. Thank you.
Yeah, the one with the hands. Right?
We just enter?
I
from falling into space.
Headed for that hexagon there.
Yep, headed for the hexagon, and it's been outfitted with ramps for you, so you can just jump up onto it.
Oh, I see the ramp.
So yeah, if you can get up on the ramp. I think you can get on from all sides. There you go. Once you're up on the ramp, everybody will be able to hear you everywhere.
Okay, am I up there?
Yep. Looks like, oh, yeah. Are you up there? I think you are. Yeah. Okay. Now let's test your voice.
Okay, do you hear me well now?
Walk away from you and see if I can hear you up here. Say something. I'm going to share the screen so we can test out your slides.
Oh, I see a little screen there.
Yeah.
Fascinating to me. I'd like to be able to say, here's my family history, and it goes all the way back to the Big Bang. There's always been this philosophical question about, well, life is really complicated. How was it possible that random chance could have done that? That's an interesting challenge for philosophy as well as for science. Well, we calculated that if the telescope were pointed at a region in space and just given a time exposure, that we would be able to pick up the signal from a bumblebee at the distance of the moon. There's a chance to see something that's very faint, some kind that nobody has ever imagined. What could that be? Well, one speculation I have, which isn't so completely ridiculous scientifically, is that the early universe produced a population of these objects, and none of them are left. Mostly, you think, well, if the universe made some of them, there should still some of them should still be here, so we could find the survivors. But what if there are no survivors of that first generation of really little faint things that maybe we could still see? So that's one of my guesses and speculations of a possible surprise. And we have plenty of inconsistencies in the evidence that we have about the early times.
Yeah.
Another area where I think we could get an interesting surprise is in planets around other stars. Everything we know there has been a surprise. We hardly were able to predict anything about what actually is. And so it's not like we don't have enough imagination. We didn't take our imagination seriously.
So I hear my voice coming back about a second delay.
Imagine it. My general principle for where to look for things, as long as you have a story that says it could never happen, because we can't imagine how it could happen, that's not a good story.
Do you have
it just means we don't have imagination. So keep looking.
I have earbuds on.
What we're about is
so maybe just reduce
all the things we don't know,
bit.
Which is almost everything. Obviously, we have two immense mysteries in science about dark matter and dark energy.
Just the volume
we might get a surprise there too, but that's harder to do. You can't picture that one.
Yeah, I'm not hearing my voice now.
You can't see them. Nothing we ever imagined lets us see them directly, but we can still try to calculate them. The first thing that's going to happen with the telescope is we launch it, we get it into focus, and we take beautiful pictures. And that will be a breakthrough in itself, a scientific, technical team breakthrough. So getting great pictures is a huge, huge, huge accomplishment. One thing that's a little startling for people is they see those gigantic golden mirrors and they say, well, that's a lot of gold, but it's not. I think they told me that it's about a golf ball size blob of gold. Gold is not a good structural material. It's very soft. Purpose for us is it's a good infrared reflector and it doesn't tarnish. So we just need a teeny weeny bit of it to cover the structural material that's beryllium. What I love is creating something new. When we say this is our dream, we want to see all these marvels of the early times, we actually have a story that can do that. Scientists say this is what we need, and the engineers say, yes, we can do that for you. That's a great, great conclusion to a long dream. Why are we here? Well, the truthful answer is random chance. Our life is inescapably probabilistic and chancy. Then you say, well, people don't like to be here for no purpose. And then I say, well, it's up to us. What is our purpose? I have purpose, which is to work on these things that I like to work on and to help along the projects and the people that I think are important for the world. If we can avoid the oncoming catastrophes, see if we can discover enough science to keep going, and basically be part of the community that we are here. We are like the agar on which the bacteria grow. The memes are propagating. They're zooming around at a speed of light between all of us, and that's just the human-centric part. The natural world is full of stuff going on too that we're completely unaware of. There's no reason that I have ever heard of why we should be that different from horses and amoebas. We're more complicated and we're bigger, but that doesn't mean we're better adapted to our world. The amoebas will be here after we're gone.
You have your robot right now.
People want to know, are we alone? That's the first big question. Personally, I think we have one observational data point, which is that here on Earth, after we got an ocean, it didn't take very long, like geologically speaking, a few 100 million years before we have evidence of fossil life. So in other words, after conditions are suitable, it doesn't take long for life to turn up. Then the process of coming to us, which requires many, many biological innovations, has taken the rest of time. So conclusion is small life, very common. Big, intelligent life, like us, very rare. Is there anybody out there trying to send us a message? Probably, but they're too far away for us to notice. Fermi asked the question, well, where is everybody? They're probably out there, but they're too far away for us to ever know. So far, we've not found any way around the difficulty of space travel. Far is pretty far. I think the most likely occurrence is that we're going to continue with a very rapid expansion of human civilization and come to a dramatic end. That's a possibility. There's also quite the possibility that we will find a way around the dramatic end. Both are quite possible, and we don't know what's going to happen. You cannot possibly tell. Also, it's pretty clear that scientists and engineers have everything to do with what turns up. We have far more influence than we know. So keep on going with the science. That's what I think. I'm John Mather, and my position at NASA is Senior Astrophysicist at NASA Goddard Space Flight Center, and also Senior Project Scientist for the James Webb Space Telescope. My job is to coordinate the connection between scientists and engineers, so that the scientists have declared what they want us to do, and engineers are able to do it. And so we make sure that it all works together. It's been my job since the first day, which was now, I think, about October 31st of 1995. As a child, I was very interested in science and physics, astronomy, electrical engineering, especially electronics. Were all very exciting to me.
Okay, cool.
Fossil collecting.
So let's get started. Hello and welcome. I'm Maggie Nassari. I'm the social media lead for the James Webb Space Telescope. This is my 17th year on our mission, and what a year it has already been. When I first started on this project, there was no hardware. It was just a vision. I was lucky enough to watch the mirrors and instruments come together at NASA's Goddard Space Flight Center, and we just launched on Christmas Day 2021, and now here we are getting our telescope ready to do science. I want to give you a little intro to our mission and our connection with art. So Webb is a really big infrared space telescope, and to see the things that we wanted to see, like the first galaxies that formed in the early universe, for example, the telescope was given a giant gold-coated mirror, and the gold actually helps it to reflect infrared light really well. But it's also beautiful in a way that's maybe not typical for scientific hardware. I've definitely heard other telescopes described as something only an engineer could love, but I thought this telescope was something artists could really love, both because of its beauty and because of the inspirational things it's going to show us. So back in 2016, when the telescope was at Goddard, I actually organized an event where we invited artists to apply to come see our telescope in person and sit in front of it, talk to mission experts, and be inspired to create art. And as it turned out, the telescope did inspire art, and a great deal of art. We actually had an exhibit of it at the NASA Goddard Visitor Center in 2017, and some of our artists kept right on creating work inspired by our mission. The art that was in the Earth Gallery where you entered tonight is art that was created by those exhibit artists. We also, on our live stream, you were able to see some of it because the camera walked around the gallery. Several of our artists, Joan Lok, Veronica Guzzardi, and Tim Makepeace, are here with us tonight. And I also wanted to introduce another one of those artists, Ashley Zelinskie, because it was she and her team from Metaxu that created the installation that we're in right now. So I'm going to get out of your way off the podium so you can speak, Ashley. So tell us about your original art for our exhibit and then about what you've created here.
Okay. All right. Can everybody hear me okay? We do?
Yes.
Excellent. So hi, I'm Ashley Zelinskie, and you're standing in Unfolding the Universe, a virtual reality experience inspired by the James Webb Space Telescope. So I was one of the lucky artists that Maggie was talking about that got to see the James Webb Space Telescope while it was in its clean room at NASA Goddard. And it is just a gorgeous piece of equipment. Besides the fact that it's going to do some amazing science and really lead humanity into the future and answer so many questions about our universe, it's also just beautiful. It's got shiny gold mirrors. They're all hexagonal. And so when I was at Goddard, I created this piece. Mostly my sculptures are 3D printed sculptures inspired by science and technology. So going with that theme, I created a work of art, a sculpture that was actually plated in NASA gold. And you can see it behind you if you're in VR, the hands with reaching out of the main telescope, the mirrors. That actually exists in real life. I 3D printed it and gold plated it. And that was on view at the NASA Goddard Visitor Center. But due to COVID restrictions, when we decided we wanted to do something to celebrate the launch, we were limited in what we could do. So Maggie and I cooked up this plan to do a VR world where we could all meet together and experience the artwork together. And this is what we came up with. So the space, my contribution was building the space with my amazing team here in Air2, and also streaming tonight with us, Carlos and Ryan. But yeah, the inspiration for this world, at least, was I talked to a bunch of scientists, engineers, administrators on the James Webb Space Telescope team, and I wanted the launch event and launch installation to be more about the people behind the mission, like all of these people that worked countless hours over the past decade to create this amazing telescope. And I wanted to feature them and really get into their experience with the James Webb Space Telescope and what it meant to them. So after doing all of these interviews, I recorded them and I did portraiture, which can be found throughout the gallery here. And you can actually walk up to the portrait of the scientist or engineer, and you can hear little clips from their interview with me. And we got into the really nitty gritty. It wasn't just, oh, hi, who are you? What's your job? You know, like, what do you do for the project? It was, you know, I wanted to get the more emotional, like, how are you feeling since launch? What do you think we're going to find with it? What in your wildest dreams do you think could be out there? And really tried to tap into the emotions that were surrounding this just amazing project and amazing creation of the telescope. So I'm going to pass it off to one of those amazing people, John Mather, and he's going to talk to you about the James Webb Space Telescope. And then afterwards, you can walk about the gallery and interact with the portraiture and hear a little bit from the other people on the team. So I'm going to pass it back to Maggie, and she can intro John. Thanks for coming, everyone.
Okay. Here I go. Can y'all hear me? I think I'm back on the podium. Okay. So I did want to just add that since that art event and exhibit that we did, we've had 2 different public art campaigns where you can send us art inspired by the science or engineering of the mission or both, and we might share it in our web gallery or on our social media. So if any of you out there are artists, send us your art. You can use the Unfold the Universe hashtag on social media. You can email us through our website. So we have had hundreds and hundreds of submissions from the public, and it's just been so amazing being able to share our love of this mission and to, you know, have people share their love of it and, you know, express it through their art. So it's been really special, and if anyone else out there wants to contribute to it, we'd love to have you as a part of it. So without further ado, I want to introduce our special guest, who is a big supporter of art and outreach and is always up for trying new and different ways to talk to people about our telescope. Dr. John Mathers is an astrophysicist, and he's Webb Senior Project Scientist. Additionally, he was awarded the Nobel Prize in Physics for his work on the Cosmic Background Explorer mission, and the measurements from COBE provided important evidence for the Big Bang Theory. So here's John to talk about opening the infrared treasure chest with JWST.
Well, my goodness, thank you. Thank you both for all the introductions. The telescope is indeed a work of art and is well deserving of all of the attention that the artists have given it. As we have designed something that looks beautiful to the eye, but entirely because that's what it has to look like in order to do the job that it does. So I think we've got a set of view graphs that we're going to show you here. And so if I'm looking at the right thing, we're showing you the chart that says opening the infrared treasure chest with JWST. So I want to talk about why that is, who is doing it. So in the upper left, you see our little symbols for the 3 space agencies that are doing this project together. NASA is the largest partner, but we have big contributions from Europe and Canada, and without them, it wouldn't be the same. We're very pleased that we're able to work out an organization and an agreement about who does what on this huge project. Basically, it's on behalf of everyone here on Earth. There are about 10,000 professional astronomers who can use it, and some of them haven't been born yet. There are about 10,000 engineers and technicians and managers that it took to build this beautiful thing. And anyway, it's been going since the first concepts were being discussed with me in 1995. So 26 years plus. And it's a little while yet before we're ready to show you all the great new discoveries that we hope to be making. So I just want to show you in the next chart some animations that show how we actually produced the observatory. So the first thing we had to do was to put the telescope together in the clean room at Goddard Space Flight Center. This is where artists came to look at it, and there's a picture in the upper left corner showing what it looked like at the time. Now we have to push the little button and advance the things one by one, but that's the picture in the left that was seen by the artists. If you push the button again, then you get to see what the telescope had to do. We dragged it over to a shaker to simulate the launch environment, huge noise and vibration that it will did experience during launch. The next little image shows you that we let's see, we have to advance it over here. We put it in the big mailbox, a shipping container that was just barely able to go around the highway over to the Air Force Base, and we put it into a giant aircraft called a C-5C. It's the biggest military aircraft we have. The truck and the container and everything went into that. And so then we pushed the button again, and there's the big airplane flying, although that's not necessarily the one we had. It flew the telescope down to Houston, Texas, where we, of course, have Johnson Space Center. And we put our telescope, that beautiful thing, into a vacuum tank. This is the very same vacuum tank that we needed and built for the Apollo astronauts so long ago. We landed on the moon in 1969 after the astronauts had practiced walking down the ladder in the vacuum right out of their landing module. So we had to, of course, improve the vacuum tank, and this was all accomplished during the middle of a hurricane. Hurricane Harvey was pouring down 4 feet of rain on the outside, but the telescope was safe inside. And next little bit will show you that we put it back in the airplane and took it on to California, where it was merged with the sunshade, which you see here. It's a giant kite-shaped thing of 5 layers of metallized plastic. When we were done verifying that it would still work when it's all put together, then we put it into the motor navi colibri, which means hummingbird in French. It's an official transport boat for rocket things to go to the rocket base. And we took it to Kourou, which is on the north coast of South America, and there we dragged the telescope out of the boat again. We put it on the rocket, and then as was mentioned, on Christmas Day, they pushed the button and up it went. So it is now all unfolded in outer space, as the final image on this little bit shows, and it was to me a completely awe-inspiring, breathtaking accomplishment to see the result of some words and some sketches on a whiteboard. It turned into 6 tons of amazingly complicated stuff, all, as far as we know, working fine in space. So on next chart, we just have a couple of images as it was before it went up. There it is in the clean room in French Guiana. Next chart will show you a picture of the launch. The part that we could see was quite short, because there's a cloud deck above the rocket base, and pretty soon the telescope and the rocket are going up through the clouds and you can't see them anymore. So beautiful thing to imagine, the tropical rainforest into outer space. Next picture shows you what it looked like as it was just leaving the rocket. They put a camera at the top of the rocket to get a picture of us as we were leaving, and there we are. Moments after that, the solar panels came out and we were good to go. So next, let's show you a movie. This is our version of a scary movie. People landed the Mars rover, and it took, as they called it, 7 minutes of terror. And they were even more terrified than we were, because if something was the matter, they couldn't fix it. In our case, we were able to go step by step, unfolding the observatory by remote control. And if anything had not worked, we had a backup plan. Basically 2 of everything that makes it possible to do as we need to do. So then we unroll the covers on the sunshade. And finally stretch the sunshade out. Separate the 5 layers, and we do all of this amazingly complicated thing in order to do one very special thing. And we need the telescope to be extremely cold. So why do we want it to be extremely cold? We want to be able to observe things that you cannot observe with the eye, that are just too cold themselves and do not emit visible light. But if we need the telescope to be so cold that it doesn't emit its own infrared light. So that's why it's so amazingly complicated, and also, by the way, the need to see infrared is the reason that it's coated with gold. Gold is the best reflector for infrared light. So it's gorgeous, and I hope you were able to see the movie as we imagined it here. We're going to come back and see now we've got a sketch showing you where did we put it. We put it around a place called Lagrange Point 2, which is about 1 million miles farther out from the sun than we are on Earth. So it's 1 million miles away from us. We orbit around it, and that's a nice place to go because it doesn't get any farther away from the Earth, and it moves with the Earth around the sun for the rest of the mission. So this was figured out in 1750. by Leonhard Euler, who had a pencil. Next chart shows you where we are on getting ready to take those beautiful pictures we're aiming for. The graphic says we launched it, we adjusted the orbit, we unfolded it, we turned on the near-infrared camera, and we started taking pictures. So we are now in the process of focusing the telescope for the first time. We had to identify the images that were formed by the 18 individual segments of that big hexagon, and then superpose them. So we're just in the process of doing that. So every week you can see our new announcements on the blog. If you Google JWST blog, you can read what we release every week. So pretty pictures coming today and tomorrow. And it still will take another 4 months before really done doing all of this. But anyway, we're very thrilled to see how well it's working now. So in around the summer solstice next summer, we will be showing you beautiful pictures. So on the next chart, we'll show you how does the telescope work. Basically, light comes from the distant universe, bounces off this big concave mirror. It focuses down to nearly a point. Before it quite gets to that point, we intercept it with a convex mirror and send it back into the instrument package. So that's a sort of standard telescope design. What's different for us is that it's an extremely stubby telescope as telescopes go. So we have to have a third mirror to make it even more accurate. Tricky thing about this one, which is sort of described in the chart, is it has to work right when the temperature is 40 Kelvin. That is to say 40 degrees above absolute zero. And that's hard to do. You cannot sort of polish it when it's cold. You'll have to polish it when it's warm and then cool it down and see if it's right. Well, of course, the first time you do it, it's not right. So you measure, warm it up, polish off the bumps you don't want, cool it down one more time, and then it's perfect. That's what we did. And nobody had ever done that before. The next chart shows you our first selfie. This is a picture of the mirror itself. We set up the camera inside so that it can focus on the mirror and not on the sky. And so here it is. One of the particular mirrors was just aiming at a particular star, but everything else is sort of lit up there too. So you can see that the mirrors are all there. They're not all in focus yet at this point of the adjustment, but they're all there. And the next chart will show you a list of the instruments that we have. So when we designed this apparatus beginning 26 years ago, we didn't know for sure what science was going to be open. We had to design an observatory that was multiple purpose, would serve all astronomers. And so basically we said, what can you do that can never be done from the ground, that can never be done by the Hubble Space Telescope? So we said, we'll set the wavelength ranges that tells you about. There are a couple of things that tell you what wavelength is, what wavelengths you can study. One is what kind of detectors can you get? And the other one is how cold can you get the telescope? So those two major features told us we needed to have cameras and spectrometers that will cover the entire wavelength range from 0.6 microns, which is red, and you could see that with your eye, all the way out to 28 microns, micrometers, which you certainly could not. And so that's a very general purpose thing. So we take pictures, we also take spectra. So a spectrum spreads out the light of a star or a galaxy into a rainbow. Of course, it doesn't look like a rainbow to an electronic chip, but we turn it into a colored rainbow when we get it back, or we turn it into a graph so it can be interpreted by humans. But the point of spreading it out into the colors is to, number one, tell how hot is an object. Number two, tell us how it's moving. Could be moving away from us very quickly. And three, tell us what's inside. What are the chemicals, elements, and molecules that might be inside? So all of those come from the information spreading out the light into a rainbow. Three of these four instruments actually also include a special thing called a coronagraph. When the moon goes in front of the sun on an eclipse, we can see the corona, which is a
hairy things that seem to stick right out of the sun. So when people said, well, we want to see that when the moon isn't there, they invented a thing to be able to see it, and that's called a coronagraph. We have our version here so we can see things that are nearby to a bright star. Well, what's interesting about little dots next to a bright star? They could be planets. So this is a special feature that we added and on purpose to be able to see planets if they're there. So now I want to show you some of the scientific themes. I have actually in the charts some graphs which may or may, I'm just wondering if I should skip over some of these because these give you engineering details. But if you have an artist's eye, you look at see, gold, beautiful colors, black. This is a diagram of the near-infrared camera. This one uses lenses, and this is the one that took the picture of the primary mirror, that selfie that you saw. Let's skip over the other technical charts here on the instruments. So, and we'll get to one that says sensitivity. So here I want to tell you about how incredibly sensitive this is. If you were a bumblebee, a 1 square centimeter object hanging out in space at the distance of the moon away from the telescope, we would be able to see you. Two ways, the sunlight you reflect and the heat you emit. So this is just a way of explaining why this is so incredibly powerful that it could do these amazing things we're trying to do. So the backstory of how is that possible? Well, number one, the telescope is very big. And number two, it's very cold. And number three, we have nearly perfect infrared detectors. Almost every photon of light that comes in gets turned into an electron that we can count. And when there is no light coming in, nothing happens. So this is an almost perfect thing. So that means it's, on the other hand, a little bit difficult to look at very bright objects, but we have our ways, taking very, very short exposures. And another special thing we can do is observe everything in the solar system from Mars on outwards. So if we have another interstellar comet like the Oumuamua that came by, we should be able to watch it. We haven't gotten there in time to be able to see the Oumuamua itself. It's gone away so quickly. It's really far away and very faint. But another one will come, for sure. So the next page, I just want to explain a little bit about the mysteries of astronomy and why it's so exciting for all of us. There are 4 great forces of physics that describe our universe and tell how everything works. Quantum mechanics was invented almost a century ago. And people looked at the behaviors of chemical elements and they said, there's got to be an explanation for this. The way that it turned out is that things you think of as point particles, like protons, electrons, neutrons, actually behave like waves. And moreover, things that you think of as waves, like light waves, behave like particles. So there's a whole lot of equations that describe this. And the upshot is that these describe the possible ways of everything combining. So how did the universe make us? Well, it's made out of little combinations of these point-like, wavy-like particles. And so quantum mechanics tells us how they stick together, how the chemistry is going to work. So we are here, you and I, because of the way that quantum mechanics makes these particles stick together. The second big thing is called gravity. Gravity is the reason that the universe isn't just a uniform cloud of gas. Gravity was able to stop the expansion of some material after the Big Bang and pull it back to turn it into galaxies and then stars and then eventually planets and a place for us to live. So we're here because of these special properties of the forces of physics. Then something called thermodynamics, which is too tricky to explain quickly, but it tells us what's going to happen and what's likely and what's not likely. So in the next chart, I just want to illustrate some of the great scientific themes that we have for our observatory. this is what we're going after, why we built such a complex thing. What is the first thing that happened after the Big Bang? Well, the universe expanded, the material was started to pull itself together. The first objects that grew from that primordial material, they turned on sometime probably 100 million years, a few 100 million years after the expansion started. So we've never seen it. We've only thought of it. So we have stories, we have ideas, we have theories, we can draw pictures, but we don't know if any of them are true. So we can see what the universe is like today. We can see what it was like earlier, but we cannot see all the way back to those very first objects. They could be different from what we've imagined. Then we think about, how did the galaxies grow? You know, the Milky Way is beautiful. It's made of 100 billion stars. And as far as we can tell, it has been assembled from 1,000 pieces. That smaller pieces grew, and then they were pulled together by gravity, and they collided and merged together, and we're just beginning to understand that too. We'd like to see this happening over the course of time. Well, of course, you can't really study yourself over the course of time, but you can look back in time by looking at things that are far away. So if you see things as they were when the light was sent to us, we can see what the universe was like when it was young. Close to home, we want to look at these beautiful clouds of stars and of gas and dust where stars are being born today with planets. The first planet stars to be born couldn't have had planets because there were no heavy elements to make it work. But now we can see inside clouds like that with the Webb telescope. And finally, we want to look at the planets that we know about here in the solar system and nearby around other stars and see what we can learn about how life is now possible here on Earth. So on the next chart, we want to show you some basic pictures. This is called the Hubble Deep Field. The director of the Space Telescope Science Institute decided that we should point the Hubble telescope at this one spot in space for 2 weeks, even though there was nothing there that anybody knew about that we should study. So nobody else wanted to point there, but he did. He said it's going to be very important because we're going to find out something new, and we did. We found out that there are far more galaxies than people had ever imagined. We found out that they formed very quickly in the early universe, and some of them, even some of the most distant ones they could see in this picture, were already old by the time that we could see them. So the almost immediate result of this picture was astronomers wrote a book and said, we need another telescope that can push farther back in time to see how did this picture happen? What came before this story? So Webb telescope is a direct descendant of this picture. So in the next chart, we just, let's skip over this one. Next chart, we show you Webb will peer into dusty gas clouds. So this is an illustration of why infrared is so important. These beautiful things that people put on the walls because they're so beautiful, they tell us how stars are being born inside these beautiful clouds. But honestly, we can't see very well. This is a story we tell more than a story we know. So we know that stars are being born in there, but the actual process is hidden by the dust. So people think, of course, space is empty, but no, it's not really. There are dust grains out there, and they block our view of the most interesting places here where stars are being born. So the infrared light that we are using with the Webb is able to go around the dust grains instead of just bouncing off. We'll be able to see much deeper inside these clouds. The next one, I show you another picture. This is, I think, an animation that shows a particular nebula changing its appearance as we go from visible light to infrared. Then I want to show you a couple of really exciting places in the outer solar system, which are exciting for the reason that they could potentially tell us something about life. Both of these are satellites. Europa is a satellite of Jupiter. Galileo discovered it himself, 1609. And we sent a mission called Galileo out to see it. And the picture that came back said, oh, this satellite is covered with ice. Under the ice is a liquid ocean. And what if it's alive? So now we know that there's water that spits out from the cracks between these great sheets of ice. And we have a mission planning that is going to go fly through the clouds of water coming out and see if there are organic molecules. That would be a very, very interesting discovery. If there's organic stuff enough, you could say it's alive, or at least we should look again. The picture on the right is a surface map of Titan. Titan is a huge satellite. It orbits Saturn. It is freezing cold out there. It's so cold that the surface is made of solid ice and covered in places with liquid hydrocarbons, ethane and methane. So there's rain, there's clouds, there's all kinds of things going on there that say, well, it's a little geologically sort of similar to the Earth. But if nature has done an experiment here to say, does life have to be based on liquid water and carbon compounds the way ours is? Well, maybe not. If it could be based on liquid hydrocarbons at a very low temperature, maybe that would work. So we are sending a helicopter to explore a little bit about this amazing satellite. So on the next chart, I want to show you something about looking at those exoplanets. Exoplanets are planets that orbit other stars. And so we have a catalog of thousands of them already, and some of them are pretty close by. But how do you know about them? These ones that we know about that are easiest to study are the ones where they happen to go between the Earth and the star. So when they do that, they block a little starlight. We can say, oh, something happened. You can say how big they are compared to the size of the star. And what we're going to be doing with the Webb telescope is analyzing the chemistry of those atmospheres. Some of the starlight goes through the atmosphere of the planet on its way to our telescope. We spread that light out into the rainbow. We do the chemical analysis, and we say, oh, there are some chemicals in that atmosphere. So we'll be looking for things like water, and carbon dioxide, and other things that might exist in planets out there. Some small ones like Earth are really hard to study. Bigger ones like Neptune or Jupiter are a lot easier, but we'll see what we can do. Do not think we're going to tell you that there's life out there, but we could tell you possibly that there are small planets with liquid water. That would be interesting. So let's see what's next here. I think I have lots more details, but I think maybe it would be better to stop and have questions from you all, because I don't know what you're thinking about and what you want to know about until you ask me. So let's stop with the presentation, Ashley, and talk to people about what they want to talk about. So, do we have questions?
So if anybody here has a question, we can unmute your mic and ask John directly, and also in the YouTube chat, if you have any questions, you can just put it in the chat, and I can repeat it to John. In the YouTube chat, we do have a couple questions about TRAPPIST-1, and then we also have a question, will you look at the strongly dimming stars?
Okay. So what question do we have about TRAPPIST-1?
Oh my God, there's so many questions. Okay.
Oh, that's great.
How long is the telescope planned to be operating for?
We guaranteed 5 years when we designed it. It looks like we might get 20. So we're very happy with that. We'll run out of fuel sometime, but probably 20 years.
Wow, that's a long time. Will Webb be able to study black holes?
Yes, Webb will study black holes. How do you study a black hole? Well, you wait to see something falling in, and then it gets compressed and hot and sends out information and light you can see. So there's a black hole in the middle of every big galaxy, and we'll be studying those. And we're very interested to see how did that happen, and when did the first black holes turn up?
Okay. When the photos come back, how will they be enhanced? And what will they be similar to? Everybody's asking about what these pictures are going to be looking like. I don't know if you can talk very much about that, but...
Yeah, of course, I don't know what they're exactly going to look like. We learned how to take pictures with Hubble and make them so that they mean something and are beautiful at the same time. So scientists need to set them up so the colors mean something. So we also have to set up so that the contrast range that you see covers the huge dynamic range that we see in the sky. So some stars are millions of times brighter than other stars, and we'd like to get them all in one picture. So we have to fiddle around with the color scales and other things that you do in editing a picture so that it's both meaningful and beautiful, so that we scientists can appreciate it and the members of the public can appreciate it too. Usually the way that we do it is we put the colors in the same order that that nature does. In other words, blue is the shortest wavelength, green or yellow in the middle is the middle wavelength, and then red in the picture will be the longest wavelength that we're looking at. But of course you have to do something like that when the human eye cannot see those colors.
Okay, we have one more, or we have a ton more, but this is the next one. What is the first object that the James Webb will look at?
Well, the first scientific object, we haven't decided exactly. We will be looking at lots of technical objects for focusing the telescope in our first 6 months of, as we call it, commissioning. And we have we are now building up a schedule for all of the observations that will be done scientifically beginning in the end of June and beginning of July this year. So, but no, we have not chosen that very first object yet.
Okay, tell me when you get tired, because there's a ton of questions in the YouTube chat.
Questions are good. All right. Thanks.
So are the internal mirrors in the instruments also coated with gold, or do those mirrors not need to be as reflective in the IR as the primary mirrors?
So yes, the mirrors are mostly coated with gold because it's easy to do and it's the best reflector. Also, the gold will not tarnish. Even here on Earth, it was a nice material to use. So yes, gold everywhere.
Will there be a possibility of studying how the Earth was formed, and we'll be able to apply it to a planet suitable for living? So yeah, can you talk about will it be looking at the Earth? Will it be studying how the Earth was formed?
Yes. Of course, we can't actually see how the Earth was formed because it happened a long time ago. What we do is we look at other objects being formed now, other new planetary systems, and we try to work out the story of how does a planetary system form around a star. So in general, we'd work on the subject of the Earth by looking at other places. Also, of course, we look throughout the own solar system to see evidence of how it works.
I think we have a question from somebody who's here in the VR space. Tim, you can unmute your mic or jump up on the stage and ask your question.
Hi, John. This is Tim Makepeace. I had a question about the beryllium.
Hi, Tim. Yeah.
Hi. I had a question about the beryllium mirrors. Is the Webb telescope the first space telescope to use beryllium for the substrate of their mirrors?
His answer is no, not quite. The United States built a mission called the Spitzer Space Telescope, and it also used a beryllium mirror, and wasn't polished quite as well. But it was a huge advance in technology. They did it for the same reason we do it, which is that it's extremely light and extremely stiff, and it behaves itself when it cools down to a low temperature.
What was the technological advance for the mirrors on the Webb then? It wasn't the addition of beryllium.
Well, it's sort of a secret recipe of the company that makes the mirrors for us. They learned how to rub just the right amount on the mirror to rub the bumps off. And then they won't tell us how they do it, but they do know how to do it.
That was Tinsley?
It was Tinsley Laboratories in Richmond, California.
Thanks.
Okay, we have plenty more. Can Webb see Pluto and beyond with clarity and with clarity without future missions? I don't know what that, I don't know. It can see Pluto. Oh, here's a good one. We have one that says, "Hi, Dr. Mather. What is the so-called hot soup we will look like if the Webb sees it? How different from CMB?"
Not quite sure what the question of hot soup means, but perhaps they're after the primordial plasma. The early universe was extremely hot and extremely dense, and it cooled off. And according to what our measurements tell us, when the universe was about 400,000 years old, it got so cool that the electrons latched onto the atomic nuclei, and then suddenly we had a neutral gas. So that's when the universe became transparent, and we can see the heat radiation that was traveling through the universe then. We now receive it here with our equipment on Earth. Then, as a long time passed and not much happened except everything got colder, and finally things started to light up because the gravity was able to pull material together to make stars and galaxies. So that's the thing we want to work on. I'm not sure it's really answered your question, though.
We have plenty more questions that we can try to answer.
Okay.
From Yasul, hi Yasul, on YouTube, she asks, if I may ask, how did you get into this field and these big questions in the first place?
Oh, well, the field that I got into is completely different from what it was when I started. I wanted to be an astronomer when I was 8 years old, but hardly anything was known in those days, and even then I couldn't learn it fast enough. So I saw the Museum of Natural History in New York. I saw the planetarium show. I saw the giant meteorite that sits there. There were all kinds of science programs for young children then. I just got to do this. And then I've been writing through this as time went along. We developed a space program, and we made bigger telescopes, and we've learned almost everything we know of astronomy was learned since I was a child. It's completely astonishing to me how exciting it is to be part of it.
Okay. Our next question is there any particular observation that you are most excited for Webb?
Oh, yes. There are two things I think are going to be really exciting. Number one, the very first objects that grew from the early universe material, whatever they were, might be different from the stories that we tell. So I'm guessing that something out there to find that we don't know about. I would be thrilled if that's true. So how would we know? Well, we're going to take pictures and see if anything is in there that wasn't expected. The other thing that really could be a big surprise is about those planets. We think the solar system might be sort of, we thought it would be ordinary and common, but actually, although most stars have planets, there are no solar systems like ours yet that we found. So we could come out and say, well, golly gee, maybe the neighbors are really far away. Maybe there's nothing but bare rocks and big planets out there.
All right, a good follow-up question to that from somebody else is, what do we know we will be able to see that we currently cannot see?
Oh, good question. Well, we'll be able to see farther back in time. because we have more telescope power and we can pick up the infrared light that comes to us from those most early moments. The other thing we are sure we can see is inside those dark clouds where planets are being born with their stars today. And so the other things that we are expecting to look at, we already know exist, but we know that they'll be looking different when we look at the longer infrared wavelengths.
Okay. What is the most significant limiting factor in how the early development of the universe James Webb Space Telescope can peak? Ooh, I don't know if that's a real question. Yeah.
So I think they're asking how far back in time can we see?
Yes. How far back in time can we see?
So what probably sets the limit is what did nature do? When did the first objects happen? And how many of them were there? So they're probably not very common, not easy to find. So what sets the limit is what did nature do and what's our best strategy for finding out? Well, here's an example. Is it better to take short exposures and cover a lot of territory, or is it better to take long exposures and cover a small territory? The first one surveys a lot of sky and looks for bright but rare objects. The second method surveys a small amount of sky and looks for very faint objects, which might just be the kind you're looking for. So we scientists argue a lot about this.
Okay, next question is, how long can we expect Hubble to keep on working with Webb?
Oh, probably Hubble can run for at least 5 or 10 more years. There's nothing that tells us it's going to stop. Eventually, the air is going to pull it back down to Earth, because it's a satellite and it feels air friction. But we have at least 5, maybe 10 or more years before that happens.
Okay, and somebody was asking, John, as a kid, who was your hero or inspirational figure?
Oh, well, I heard about Darwin. I heard about Galileo. I heard about George Washington Carver. And they were all heroes to me. I thought they have discovered things that the world didn't know before. And at least the first two, they also got into trouble because people didn't always want to hear this information. But I thought, well, that just proves how important it was. And okay, well, I want to do that. Maybe there's something there to find out. I had no idea. When you're a kid, you just can't see. But anyway, I just wanted to be part of it.
Okay, and we have another question from Matt Timms on YouTube. I've seen people around the world applied to use the telescope to see various things. What were some of the most interesting requests?
Oh, yes, we did actually solicit proposals from all astronomers. And we got a lot of interesting things well, I'll tell you one that intrigued me. It was argued that we should look at Alpha Centauri, which is the nearest star. So people have good reasons to think that it won't have planets. But what if it does? It would be a shame not to look.
All right. How will distant planets look different to the Webb telescope? I guess as opposed to Hubble or other telescopes, other instruments.
Yeah. So they all have different capabilities. The thing that I showed you already, where we can see a planet going in front of its star, we already have a big catalog of those because it's been done with other telescopes that were specially designed for the purpose. The technique of spreading out light into a rainbow to look for the atmospheric contents, that's also been done with the Hubble and the Spitzer Space Telescope. The hardest thing actually is to get an image of a little planet sitting next to a star. And the trouble with what makes that hard is that the star is awfully bright compared to the planets. The sun is 10 billion times brighter than the Earth. So how are you going to do that? It's like seeing a firefly next to a searchlight. So you can't. But anyway, that's one of the things we will try to do. And our equipment is designed for that, but just not as good as you need to do to see Earth around another star.
Oh, and here's an interesting question. How much redundancy is built into the James Webb Space Telescope? And what are the chances of a micrometeoroid hitting it and causing damage?
Okay. 2 questions. Well, number one, we have 2 of everything where it's possible. You know, electronic parts fail if you have 1 million of them or 100,000 of them. One of them will fail after a while. So you just have to have 2 of everything. So we do. The question about micrometeorites, well, we know how many there are. We calculate that the biggest one that will hit us will be about 1 millimeter across, and it'll make a hole in the sunshade, and we won't care. We're more worried about other tiny ones making holes in smaller things. So we had to wrap shields around the electrical cables and things like that. So, but that's another reason to have 2 of everything.
Okay. What are your hopes for the next decade of surveys for NASA?
Oh my goodness. Well, for this telescope, we're certainly hoping to find something that we didn't expect. We did all this work to learn something that we didn't know. If all we do is say, yeah, well, we measured a number better, that won't be very exciting to too many people. But I do expect we are going to change the story about how planets and stars grow, what happens when they get old. We're going to find out more about the very earliest parts of the history of the universe. And then after that, we hope that there will be new generations of telescopes coming along to do different things. There are some that are being built on Earth, which are enormous. The biggest one is European, and it's 39 meters across, and it's 6 times as big as the Webb, but it's stuck, of course, at the bottom of the atmosphere where we are. So there are things that get in the way, too. But that's the possibility of following up our discoveries of the Webb telescope with additional big telescopes on the ground is very exciting, too. Then, after that, we astronomers are dreaming big. We want a telescope that's good enough to see images of little Earths orbiting other stars. And that's pretty hard, but we're going to be working on it.
We're having more people join us in VR, so if you guys have any questions in the hub space, please unmute your mic and ask, or drop them in the chat in the VR space. But here's another one from our YouTube stream. How many telescopes can orbit L2 at the same time?
Pretty much as many as you can manage. The L2 region is huge. Our orbit is about 300,000 kilometers radius around the L2 point. So, all you can afford. It's big.
Okay, and another one from YouTube. What will the joint capabilities of the James Webb Space Telescope and the Grace Roman Telescope be? And how are you looking forward to the Roman Telescope? Yeah, so the Roman Telescope, we didn't talk about it yet. It is a survey telescope to cover a large fraction of the sky with near-infrared observations. So it gets 100 times as much sky at one time as the Hubble could do. So
what it's aiming to do is concentrated on the dark matter and the dark energy, and also capabilities to observe exoplanets. It would be another shot at improving that technology. So they will survey the universe, they'll tell us where to look. In many ways, they're a finder telescope for the big telescope. So since we now expect the Webb to be alive for a long time, it's plenty time enough to wait for discoveries from the Roman telescope to be published, and we'll use those and say, well, they say, look, we found this really weird thing over here. Let's go look at it with the Webb, and of course we will.
Okay, here's another one from the YouTube chat. Are there plans to send the Webb even further into space at any point? How far will it drift in space over the course of its life?
Oh, Webb telescope will stick around the Lagrange point 2 throughout the duration of the mission. And we'll fire the little rocket jets once in a while, every few weeks, to make sure that it stays there. When we run out of gas, when we run out of fuel, the telescope will be released and allowed to go into orbit around the sun. And then it'll get farther and farther away.
Okay, there's another one from YouTube. Is there a next space telescope project in development, and what may the capabilities of that telescope be?
Yeah, the one that we just mentioned, the Roman Space Telescope, is the next one for NASA. It's expected to go up in 2027, so just 5 years. Our European friends are launching a smaller one called Euclid, supposed to go up this year. So we already have stuff under construction that's going to go up. Then after that, we have Dreams.
Okay, still have more coming in from the YouTube chat. I don't know if you can see the YouTube chat, John, but it is blowing up.
No, I can't see it, so you'll have to select some good ones.
So we have somebody asking about chemical signatures of exoplanets.
Mm-hmm.
Okay. Not really a question, but just can you talk about chemical signatures picking up by Webb?
Yeah, sure. We would like to know what are those exoplanets made of. So we expect them to be made of the same chemical elements, but what will be interesting and different is, well, what chemical molecules have they got, and that'll tell us about the temperature and pressure in their atmosphere and how they might have been formed. So, for instance, if you were to take our planet Jupiter and move it closer to the sun, like the same distance that we are, it'd suddenly be a lot warmer, and its temperature would change, its internal chemistry would change, and it might even start to evaporate, or at least smaller ones would. So this is a lovely question, and it'll be a very rich subject when we get some data.
Okay, we have more questions from YouTube. Can you see James Webb Space Telescope from Earth?
Could you say that one again, please?
Can you see the James Webb Space Telescope from Earth?
Oh, yes, actually. Astronomers with medium-sized telescopes have been able to take pictures. It's around, as astronomers call it, 17th magnitude. So that's a lot fainter than the stars you can see with your eye. But it is possible to get a picture with a pretty big telescope, like a 1 meter diameter telescope is big enough to get a picture of it. There are lots of young astronomers who can do that.
I actually got a telescope for Christmas this year, so hopefully that will be me once I learn how to use it. So there's another question from YouTube. Will Webb be able to take pictures of the Earth? Would there be a reason to do so from that distance?
Answer is no, actually. We can't point the telescope at Earth because the sun would get into the telescope, and we would not like that.
Yes, that's why there's sun shields, I guess. More questions coming. So many questions coming. How will the James Webb detect the nurseries where stars are born?
Well, actually, we already know where they are. We have been surveying the sky for a really long time. What we now have the chance to do is to choose specific ones that are exciting for us because they're going to tell us something we don't know. So we will see the ones, for instance, the Hubble pictures show, where you say, I wish our word could see inside, and then we'll try those. So we have a good, nice list of those to try.
Okay. What is the longest exposure that James Webb Space Telescope is expected to take?
There's no particular limit on how long the exposure can be. We could do what they did with the Hubble telescope and point in one direction for 2 weeks. But we probably won't do that right away. You'd have to make sure that it would be worthwhile first. But there are projects that would examine the most distant parts of the universe, and that's about what it takes, a couple of weeks.
Okay. Can Webb look at a red supergiant star like Antares?
Oh, yes, we can. But that particular one is so bright, it's almost hard to study it. But yes, we can. They are everywhere. They're very bright and easy to find. And so they're interesting because they show us the end of a star's life. When a star has used up most of its hydrogen fuel and most of its helium fuel, it gets very big and red. And then, well, even the sun will do that in about 5 billion years.
Here's one from the VR chat. If a star like Betelgeuse were to explode, would we shift the schedule to look at that unprecedented event?
Oh, well, if something's important, yes, by all means. We have a plan. It takes us about 2 days to respond to a sudden event like that, which is basically almost all people time. To call us up, we have to talk about it.
And if anybody in VR wants to ask their question, just unmute your mic. You don't have to be shy and put it in the chat.
Hello.
Oh, can we hear somebody? Did somebody just unmute? Come closer to the podium, and we can hear you better. If you have a question. Anybody in here? I heard somebody unmute their mic. Okay. All right, so we'll go back to the YouTube then. Will Webb be able to capture pictures of fast-moving objects that pass in front of it, like meteors?
Well, if something goes quite fast across the picture, what we'll see is a streak. And so occasionally we do. We expect to see a great many fast-moving objects. For us, they will be asteroids and comets. So they're not all that fast because they're not that close to us. But we expect most pictures to have streaks across them from asteroids.
Sorry, just sorting through all of the zillion questions here. The chat's moving very quickly, so it's hard to keep up. Oh, people are arguing. Yeah, wouldn't Betelgeuse be too bright? Yes.
I actually have a question.
Oh yeah,
sure. Go ahead.
I was wondering if you had the opportunity to have changed Webb for the purpose of folding it up or unfolding it in the Ariane 5, what would you have changed about the telescope?
Oh my goodness. I can't think of anything that I would have chosen to change because it was hard enough to do it as it was. It's a really snug fit inside the rocket, so we're not going to make it any bigger. there are always, as you know, lots of things where you say, I got to the end and I wish I'd done it a little differently. But mostly it's a matter of making things more reliable. You know, when we were putting this together and testing it, we found that some mistakes had been made, and we had to back up and take things apart and put them together again. And you'd say, well, I didn't need a better design, I just needed to not make a mistake. So that's where, if we had the chance to do it over again, we would avoid those mistakes.
If you have had the opportunity to make the mirror bigger, would you have made the mirror bigger?
Well, we tried, actually. Originally, we specified that it was an 8-meter diameter mirror. And then we calculated that we couldn't afford it. And it would take too long anyway, and then it wouldn't fit in the rocket either. So, had to back off.
Alrighty, thank you so much.
Yeah, thanks.
That's cool. Another one from the chat. Will Webb be able to give us additional info on sun flares?
On sun flares? Yes, I suppose, but it's actually, for us, it's more of an annoyance. It's not a scientific research project for us. But sun flares blast away with charged particles, and some of them go through the detectors. And they make little sparkles all over the detectors. So if you see our visual space, our virtual space, it's all covered with beautiful little white specks. Well, if those were not real, but random additions to our image in each camera, we wouldn't like that. So we treat solar flares as a hazard.
Here's a cute one from the chat. Why is the James Webb Space Telescope shaped like a honeycomb?
Oh, yeah. But actually, part of the answer is, well, if you start with circles, and everybody loves circular telescopes because it's traditional and it also works well. But now you're going to make the mirror out of pieces. So what pieces can you use? What shape of pieces can you use that will fit together to make an almost circle? And you have three choices. Triangles, squares, and hexagons will all fit together to fill up a space. So the easiest one is the hexagon. The angles are not so sharp, and it's closer to a circle.
Okay, and here's one that's relevant to this exact experience we're all having. Do you think personally art is important to science to inspire future generations?
Well, of course. How are people going to know what we saw and how we felt if we don't actually try to put some of that into our artistic communications? If I just give you a formula, well, how many are you going to be excited about it? But if we can show you what it means in some technically correct or emotionally correct fashion, that would be important. Really important.
And that's what we're doing here. I think that's a really good question to end on, because now we can do a couple minutes of walking around the gallery space and interacting with the portraiture and the sculpture in the middle. But I do want to thank John so much for participating in this project and donating his time not only to me, but now to all of you, both in VR, which we're almost at room capacity now, and also on our YouTube live stream. We've had tons of people on the YouTube live stream. But yeah, thank you, John, so much for being with us tonight. We really appreciate it.
Well, thank you for the invitation, and thank you for setting up with such a lovely set of questions for the audience. So I love talking with you all, and hope we will do this again.
Thank you. Yeah, and we can walk around the gallery space and interact with the portraits now. And each one of the scientists that I interviewed, they have a little clip of telling about what they do and what their part of the James Webb Space Telescope project was. And you can you can go and interact with those portraits and maybe get to know the scientists and engineers behind the project a little bit better, and then tune in for their VR chat. So we have a long list of scientists and engineers that have also offered to donate their time to do one of these virtual chats and live stream chats. So stay tuned for that. Follow the NASA Web on Twitter and on Instagram, and we'll be posting more virtual reality events with the people that made the James Webb Space Telescope happen. So round of applause, virtual applause for John.
Thank you, and applause for the people who made this amazing space to work. Thank you all for the technical and programming and everything that goes into it. I have no idea how it's done, but I know it's not something I could do. Thank you.
Yes, thanks Pierre and Ertu at Metaxu Studio, and Carlos and Ryan, who have been our amazing, they're doing the live stream, and they're doing a beautiful job, great panning shots. And thank you to Maggie and Isabel at NASA for putting this all together and for being in 100,000 meetings with me over the past almost a year now. Yeah, and John, thanks so much again for donating your time. And we can go over to your portrait, and we can talk more about why you were part of this art project and getting to know everybody in the space now.
Yeah, sure. I don't know where my portrait is at the moment, but
I can guide you over to your portrait. Yeah.
Yeah,
we have somebody in the chat. Thank you for being here from Rachel. A bunch of people. Yeah, so many thank yous in the chat. Thanks, everyone.
Oh, we've got someone in a VR headset as well.
There's somebody in a VR headset. Cool. Thanks, Maggie.
Thank you so much. Thank you, John, for going along with us on another interesting trip of doing outreach in unusual ways. And thank you so much to Ashley and Metaxu for the beautiful work on this gallery.
Yeah.
Thank you. Yeah, it was
So
great.
you said I could go to my portrait, but I think I've got to go do something else now. So I will sign off.
No problem.
And thank you for the invitation. It's been fun.
Yes, thank you so much.
I'll send you.
Right.
Yeah, thanks, John. Thanks, John, for being our guinea pig and putting up with all this. I'll send you the videos and some photos and stuff.
All right. Thank you all. Bye-bye now.
Thank you.
Bye, John.
Bye.
Thanks, John. Bye.
Great. Well, that's pretty good. We were at some point 19, so I think.
Okay. Where's Carlos? Because I'll kill this live stream then.